Boyle's law shows us mathematically that as P goes up, V goes down, and vice versa. Charles's law shows us mathematically that as T goes up, or down, V also goes up, or down. And finally, Gay-Lussac's law shows us mathematically that as the temperature goes up or down, the pressure also goes up or down. What you can see here is that we've got pressure, volume, temperature, and each of these is related to some constant. And what we're going to do in the combined gas law is we're going to put all three of these into one equation. So here we go. The combined gas law merges Boyle's, Charles's, and Gay-Lussac's laws into one equation. And here it is. P1V1 over T1 equals P2V2 over T2. What this equation says is, if you have a gas at a particular pressure, a particular volume, a particular temperature, and then you change one or more of those quantities to a different pressure, P2, and let's say a different temperature, T2, then you can use this equation to calculate the new volume. For all gas law calculations, you must use the absolute temperature, that is, the temperature in Kelvin. This equation is extremely picky about the unit for temperature. It has to be Kelvin, never anything else. If the temperature is given in Celsius, change it to Kelvin, and then you'll be fine. It's not picky about the units for pressure or for volume. As long as the pressure units left and right agree, you can use any pressure unit you want. Atmospheres, torr, psi even. The same goes with volume. As long as the units for volume are the same on each side, you're good to go. Cubic centimeters, milliliters, liters, cubic decimeters, whatever. As long as the volume units agree, you can use any unit you want. With temperature, it has to be Kelvin, never anything else. So I thought I'd have a little fun here. I picked up these pictures of Charles in the lower left. In the middle, we've got Boyle, and on the right, we've got Gay-Lussac. And if we combine them, then we get this rather handsome devil. I mean, if we're going to combine their gas laws, we might as well combine their pictures. So let's try a problem. A sample of methane occupies 126 cubic centimeters at negative 75 degrees Celsius and 985 millimeters of mercury. Find its volume at STP. Right away we see a temperature that's given in degrees Celsius. So immediately we're going to change that into Kelvin because we know degrees Celsius is never okay when we're doing gas law problems. Then, although it doesn't specify what kind of a quantity 126 cubic centimeters is, nor does it specify the other quantities, we know from the units what these quantities represent. The 126 cubic centimeters is the volume, the 198 Kelvin is of course the temperature, and the 985 millimeters of mercury is the pressure. There's the combined gas law. We know that any unit for volume is okay, so cubic centimeters is fine, same with pressure. Initially, we have a pressure of 985 millimeters of mercury, a volume of 126 cubic centimeters, and a temperature of 198 Kelvin. Now what we have to do is we have to go back and think, wait, what are the values of the temperature and the pressure at standard temperature and pressure? Well, standard temperature, we're supposed to have memorized, is 273 Kelvin. And standard pressure could be any number of pressures, 1 atmosphere, 101.325 kilopascals, but because this pressure is given in millimeters of mercury, let's use standard pressure in millimeters of mercury, which is 760. So now it's just a matter of solving this algebraically. I'm going to cross multiply to get rid of any denominators. Then I'm going to divide both sides by both 198 and 760. We type that thing on the left into our calculator and we get 225. What are the units? They're the same volume units that we started with, which, way up here at the top of the screen, are cubic centimeters. So that's how you use the combined gas law. Strangely, I was never taught the combined gas law. when I was in school. I was taught what I call the thinking method. I'm going to go ahead and show that to you because I find it more intellectually rewarding than just simply plugging and chugging using the combined gas law. And here's how the thinking method works. We know that we need to calculate a new volume. So we set this unknown new volume equal to the initial volume. Now what we do is we put a fraction there and we ask ourselves, let's do temperature first. What happens to the temperature in this problem? Well, it starts out at 198 Kelvin and it ends at 273 Kelvin. So the temperature went up. What effect would an increased temperature have on the volume? And the answer is it would cause the volume to increase. Therefore, I need a fraction that is larger than 1. Therefore, the 273 goes on top, the 198 goes below. We'll do the same thing now with pressure. Pressure started at 985 millimeters of mercury. It ended at 760. If the pressure has decreased, what must have happened to the volume? It must have gotten bigger. So the pressure quantities will also lead to the volume getting bigger. And you can see that we have at the bottom the same fraction that we have dead in the middle of the screen. 985 on top, 126 on top, 273 on top, and in the bottom 198 and 760. You get, of course, the same answer.